Hello, my name is Giancarlo Tonday Rodriguez, and this is going to be my presentation on a facial detection lock for TCN 5060. So, my design is supposed to be an IoT-based design on something that is easy to install and simple to use. This is generally uh, a standard term for IoT devices, as most of them as they have seen a tremendous rise throughout the past couple of years, and they're expected to continue rising up to 2027 and even beyond, as can be seen in this particular study, in this particular analytic, that it's expected to rapidly, the market share is supposed to rise. Other studies can have them going even higher, up to 2030 and even beyond. IoTs generally see this popularity increase due to their usability and ease of use. Most of them generally only require a certain command or have very simple user interfaces and methods of installation that anybody can pretty much set up and install and use on the same day. Things like Amazon Alexa, Google Home, and Ring, the Ring doorbell, among others, have generally been the primary product of these rapid increase, as they are becoming very commonplace in most American homes. Again, the important fields in this particular rise have tended to be things like smart sensors, so smart thermostats, smart homes like with smart appliances like smart TVs, smart refrigerators, interconnectivity between those, as well as smart microphones, which generally can tend to be hub-like in behavior. So things like Alexa and Google Home that may be able to control different houses, different house factors like lights and locks and the smart and timers, and even just general browser search has become much simpler and universal throughout the use of these smart microphones. And then the primary topic of my research project was primarily home security, which are things like Ring doorbell and smart locks and ADT security, which have seen a lot of rise because home security is something that's very sought after, and these technological advances make them very simple, very safe, and very usable by anybody. Generally, the issue tends to be sometimes price, and it's other times it can be things like they're not very usable. Generally, they have a lot of different parts, then they don't really coincide together, or overlapping parts that I look to change in this project. So the main point of that I did this design was to be able to combine different parts of different home security designs together, like a camera recognition software, and then a lock system included with that camera detection. But the main point of it is that it has to be reusable. It has to you should be able to swap locations very easily with it. It shouldn't just be locked in place, and it shouldn't be a very large object that is not carryable or not transferable. So therefore, the best aspect, if you want to make it have a very wide location, is to use a wireless-based communication in between devices for simple installation and use, as you don't want to have the hub, which might be bigger, heavier, and more computer intensive, to be in a place that is not, it might be obtrusive in, like, for example, in the middle of a doorway. And again, the main factor was improving the security aspect. I want to make it so that you can combine these different security aspects together and have a more in-depth design. So the standard design, again, we're going to be using a wireless implementation, particularly a Wi-Fi protocol implementation. We're going to be using Wi-Fi for this, and we want it to be powerable through multiple methods. In this design, we are going to power it through a permanent power solution, so connected to a plug, an outlet, or a device that might provide a lot of power or a lot of battery life to it. But however, we can also use a short-term battery solution for in case the power goes out or something like that, you still have a battery solution for the yeah, for the camera and lock unit. We want it to be fast answer. So once you click it, it actually goes straight to it, and it gives you a quick response. That it doesn't take a minute or 2 minutes of processing, and we want it to be pretty much on demand. You don't want it to pretty much shut down or the server is unresponsive. We want the server to be as responsive as possible and as usable as possible. So whenever we call for the camera to take an image, we don't want it to either not have power, or maybe at this point it's in a sleep mode and it cannot take the image at this point. That is not really a useful design for it. And to do so, we have to split into three main sectors, and it's going to be each of their wireless each of our wireless connections, which is running its own separate line of code, separate code instances or coding scripts. This is the unlocking mechanism, which is the majority of our program. The locking is very simple. It's just a request to the sensor to lock unit to lock the door. In this case, this is a or flow chart or flow diagram. We're gonna have the central processing, which is done through the laptop through our web app. Once you begin the unlocking, you're going to you're gonna start a timer, and every 30 seconds, you're pretty much gonna check. You're gonna check if it has detected a correct face, and then it's going to not run it anymore. But every 30 seconds, you're gonna send a request to take an image to the ESP8266 on the camera unit. The ESP is then gonna forward a image request to the camera picture via serial connection, which is gonna send the image back out through the same serial connection, but it's gonna be a different instance or at a different power than the send request image. Once you get the image back, it's going to store it locally on the ESP8266 via the SPIF system, which is then going to send it to the laptop to process the image using the library that will be used for this, which I'll cover later on. And then it's going to run the face recognition software. If it says yes, then we're going to activate the servo, and we're going to kick out of this, and we're going to change our web page to reflect that the system is now unlocked. Alternatively, if it's not, then it's going to go back to the laptop, to the timer. It's going to wait the 30 seconds, and then it's going to call for another image. In this 30 seconds, just expected that a new person should have, the person that was there should have already reaccommodated, and maybe if it's their home, he should already be there. If not, then he should have left. So this is our camera unit. Our camera unit is going to be the ArduCam Mini 2MP connected to an ESP8266. Those are the connections generally there. The ESP8266 is what I want to cover first. It is a Wi-Fi enabled chip. It's going to be able to access Wi-Fi communication, and it comes with its own microcontroller, and it comes with its own SPIFs file system, which again, those are the three major things. You want a microcontroller to be able to control the camera, a Wi-Fi chip in order to be able to communicate with the computer, and you want the SPIFs to be able to locally store the image before it's transferred out via an HTTP connection. The camera is the most expensive part of this entire design. It is around $20 worth of price, but you're trading in the price for the functionality. The camera provides very high picture quality, which actually helps us more easily detect who the person that's taking who the person that is at the camera who has requested the image is. Given that you can pretty much it's pretty much necessary, as the cheaper the camera, the less the picture quality and the less effective it is on the algorithm in order to work. The ArduCam is also supported by the Arduino IDE, or IDE for both the camera unit and the lock unit, as both of them are going to be running their scripts on the microcontroller of the Node MCU, which is a Arduino based chip. Again, our Arduino IDE runs the Arduino programming language, which is a variation of C. So essentially, it is like writing a C code with a couple of built-in functions that are very useful, particularly for controlling this Arduino and some of the peripherals that it contains. So for a processing unit, it's going to be, it can be actually any device that can run Windows, because the code was written for particularly Windows devices, but it could be changed, modified to work for Linux-based devices. In this case, I use both my computer and my laptop in order to demonstrate it. It's gonna use Python 3.9. So the code is running on Python 3.9, and it's gonna be running on Flask for the web application, which is the web application is gonna be running out of your processing unit. And it's a simple to set up web app for pretty much all devices on the local network. So you just run the web app, and it should be viewed or viewable to all devices on the local network, given that you know the IP of the processing unit. Yeah, it needs to be able to run pretty much some kind of machine learning based algorithms, because we're going to be running uh, facial recognition functions out of the dlib library, which is a certain machine learning library. And then we can, it should be able to contact both of the other units on demand, given that both the other units are available at that point that it is sending the contact to. So for the lock unit, the lock unit is again going to be running a ESP8266 node MCU, and it's going to have only the lock connected to it. Again, the node MCU is going to be the one receiving the power. The servo is going to be connected to the node MCU, and it's going to be receiving power from the node MCU to do certain rotation indexes on the servo, so it can rotate 90 degrees and 0 degrees. And that's pretty much all you needed, because 90 degrees will be your unlocked state and 0 degrees will be your locked state. So once it receives a signal from the node MCU, it'll be that it can run this. Just to clarify on the processing side, the IDE I will be using for the processing, it's going to be running on Python 3.9, but we're going to be using the Visual Studio Code IDE due to its simplified use for Python coding. But any Python IDE any Python IDE or working environment can generally be used. So for the software design, we're going to be, again, using a centralized design. The app is going to be pretty much controlling everything, and all of the others are going to be working like waiting for a request from the web application, which is going to be running on your processing side. So once it receives a request from your web application, then it's going to kick out the web app. So for the camera software, we're going to be using certain libraries for the network communication. So we're using, this can be divided into two parts. One is the network communication, and two is the local or serial communication. So network communication, we're going to be using ESP8266 Wi-Fi, ESP8266 web server, and of course the client, the web client libraries, which are all useful for sending a communication out through a Wi-Fi signal. And then we're going to be using the some serial transfer with like wire, like SPIFs, like SPI, and like the ArduCam library, in order to be able to take the image from the camera and pretty much do a serial transfer of it into our ESP8266 local SPIFs file storage system as a JPEG file, which is then going to send it out using the networking libraries like ESP8266 web server, which is going to get a request from an external source. In this case, it will be our primary processing program to get an image, sends out the image, and then download, and then it can pretty much wait for another request. As for processing software, we're going to be writing it on Python, and the two main libraries that we're going to be using is Flask and face recognition. Flask and request are going to be used for connecting, for sending a request. For Flask is used for the web application creation, and request is used for pretty much receiving or sending a request to the two other devices. And then face recognition is going to be your face recognition library, which is built on top of dlib. It's based on dlib, and it's going to be used for face detection and or face recognition. And face recognition generally works on using face encodings, which come built in with the face recognition library already, in order to be able to pretty much encode an image or file.jpg, which is again our already existing personal image that we're trying to compare it to, and our face to recognize, which is the face that we're trying to recognize that we received from the camera unit. For lock software, we're going to be using again the same networking functions as for the camera unit. We're going to be awaiting a request. Once we receive the request using ESP8266 web server, we're going to pretty much decide whether we're going to lock or unlock the key. If it's unlocked, then we unlock it, rotate it 90, and if it's locked, then we're just going to rotate it back down to 0, which is locked state. So for the evaluation, the app runs very well. This will be shown in a little bit. It is a web-based app, so we're gonna be, we can use a phone to activate it, or we can use my own computer, like I'll show later on. It is a simple to use app. There's only 2 buttons. As you can see, there's an unlock and a lock, and it's very much self-explanatory. You click on lock, it's gonna unlock this. It's gonna send the unlock sequence, which is gonna require an image verification, and if you click lock, it's just gonna lock it. And the peripheral units are pretty much simple to set up. You just need to connect them to power. They're going to reset, and they're going to self and auto initialize to open the web server and open and auto lock the lock, and then open the lock server as well. So there's 2 major drawbacks. One is the battery usage. These are not very good for battery usage, again, because they need to be on demand, and because they're running on Wi-Fi, they actually consume a pretty decent amount of power, and some other lower power protocols might not really consume. So this is something that needs to be worked on. And the other thing is a couple of security risk. The networks for both the lock and the project net can already be seen, and they don't really have a password or anything, but that can be changed by adding a password mechanism to them and hiding them, making them hidden, so that only the web application knows what they are and how to contact them. So in conclusion, my project is designed to improve the accessibility of some of these locks and some of these security systems by combining them together and making them more generally usable. It's supposed to be simple to use and pretty much require very minimal installation, only needing you to download the app and pretty much just run it on a web server based out of some kind of server or some kind of hub device. And then it's pretty much accessible and easy to use because it's only 2 buttons on a web app, and they're pretty much self-explanatory. So here's a presentation of the app, and its current state is in an unlocked state. The lock is currently unlocked, and then I'm gonna click lock. Now it's currently locked. As you can see, the web app and the actual lock are both synced. If you click on lock, it's going to take an image, but in this case, I'm going to have my phone covering my face so that it doesn't recognize me. Now it's going to take the image and nothing happened. That's because my phone is covering my face and there's clearly a failed. It's false. The face was not found. They couldn't really recognize anything there. So if we click on lock again, but this time we do it correctly. As you can see, I'm just moving the camera away so it can be noticed. It's going to unlock. It says unlocked on our web server, and if you look at the image, there is nothing covering it. It recognizes it perfectly. That is essentially how it works. It can work from your phone, given that your phone is connected to your local network, and it can work from any other device connected to that local network. That'll pretty much be it for my presentation. Thank you for your time, and thank you for hope you guys have a good rest of the semester.